All right, today we're going to pull back the curtain on one of the most powerful, most influential statistical tools ever created. Seriously, it's a method that quietly shapes pretty much everything, from the news you read to the tech you use every single day.
But here's the thing. This tool is a total double-edged sword. On one hand, it can uncover these profound truths that are just hiding in plain sight within data. But in the wrong hands, or, just used carelessly, it can lead to some wildly misleading conclusions. And that's exactly why understanding how it works is so critical.
So what's the fundamental problem we're even trying to solve here? Well, we're just swimming, maybe even drowning, in a sea of information. So how do we find the signal in all of that noise? How do we take this chaotic cloud of data points and turn it into something that can actually help us predict what's going to happen next?
Well, one of the best answers we have is regression analysis. At its heart, it's just a way to formally describe the relationship between things. That's it. We just pick one thing we really want to understand, we call that the outcome, and then we see how it changes when other things, the predictors, change.
Okay, so let's start with the most basic version of this idea, the one you probably remember from a high school math class. It really is all about drawing a line.
So just picture a graph with a whole bunch of scattered data points, like a cloud. Linear regression is all about finding that one single straight line that gets as close as possible to all of those points at once. Now, this best fit line, it isn't just a pretty picture, it's actually a mathematical model. It gives you a super simple equation that basically says, hey, if you tell me X, I can give you a pretty good guess about Y.
But, reality is rarely that simple. Things are messy. They're not always a straight line. So how does this tool adapt when things start to get a little more complicated?
Predicting a number, like a person's height or weight, that kind of makes sense for a straight line. But what if the outcome you care about is just a simple yes or no? Like will a customer stay or will they leave? Does a patient have a certain condition or not? A straight line is totally useless here. It could predict values that make no sense, falling way outside our simple yes or no options. And this is where we have to pick a different tool for the job. It really highlights the key difference between linear regression and something called logistic regression. Linear is for predicting those continuous numbers, like a measurement. But logistic, that's for predicting which category something falls into, a yes or a no, a win or a loss. It tells you the probability of an outcome happening. To make this really concrete, let's dive into a classic study from the Journal of Marriage and the Family. Researchers wanted to figure out what predicts whether a person reports being not too happy. So the outcome here is a simple yes or no category, perfect for logistic regression.
So instead of a straight line, logistic regression uses this really elegant S-shaped curve. And as the author of this paper, Alfred Damaris, points out, it's a totally natural fit. Why? Because the curve is always squished between 0 and 1, just like a probability. It's brilliant, really. No matter how much your predictors change, the model can never, ever predict a probability less than 0% or more than 100%.
And the results from the study are just fascinating. The model let the researchers isolate the impact of all these different life events. For instance, after accounting for everything else, the odds of being unhappy were 3.5 times higher for widowed people compared to married people. Good health had this massive protective effect. Meanwhile, a recent trauma made unhappiness significantly more likely. And that's the real power here, turning this messy, complex data into clear, understandable insights. Okay, so we've gone from simple lines to these cool S-curves. But modern data throws a whole new wrench in the works. What happens when you have a truly overwhelming number of things you could possibly measure? Think about trying to predict stock prices. There are thousands of possible variables you could look at, right? If you just throw every single one of them into a traditional model, you risk this huge problem called overfitting. That's when your model gets way too complex and it starts modeling the random noise in your data instead of the true underlying pattern. It looks amazing on your past data, but it completely fails at predicting the future.
So, how do we deal with that? Well, this is where a newer set of techniques, often from the world of machine learning, come in. They're called penalized regression. Basically, these methods automatically simplify the model for you. They work by adding a penalty for complexity, which forces the model to ignore all the noise and focus only on the variables that actually truly matter. Now, there are a few main flavors of this. You've got ridge regression, which kind of shrinks the influence of all your variables a little bit. Then there's lasso, which is way more aggressive. It can actually eliminate unimportant variables completely, shrinking their impact all the way to 0. It basically does variable selection for you. And then elastic net is a hybrid of the two. In a study that was trying to predict stock returns, Lasso was the clear winner, precisely because it was so good at automatically filtering out the junk and just focusing on what was most predictive.
All right, so we've got these incredibly powerful tools. But like we said right at the beginning, they can be a double-edged sword. So this next section is absolutely crucial. Think of it as a field guide to the most common mistakes and traps based on warnings from people who do this stuff for a living. This is the big one, the cardinal sin of statistics. Regression shows you that two things move together. It does not, by itself, ever tell you that one causes the other. It's a classic mistake that leads to some totally absurd conclusions.
Next up is using the wrong tool for the job. We already saw this, right? You have to match the model to the type of data and the kind of question you're asking. Trying to use a simple linear model when your data clearly isn't a straight line, or when your outcome is a count of something, you're just going to get garbage results.
Oh, this one is so tempting. There's a metric called R-squared, and it basically tells you how much of the story your model explains. It feels really good to get that number as high as possible, but the trap is you can artificially pump it up just by adding more and more variables, even totally useless ones. It's a classic sign of an overfitted, unreliable model. And this quote from a statistician on Reddit just says it all perfectly. Your model is not your data. A regression model is a simplified map of reality. It is a lens to look at your data through. It is not a perfect mirror. You have to remember that distinction. And here are a few more quick-fire mistakes to watch out for. Not cleaning your data first. Garbage in, garbage out. Forgetting to check the model's basic assumptions. Getting confused by how different variables interact with each other. And a personal favorite, just blindly believing the universe is made of straight lines. Because it usually isn't. The real bottom line? If you can't explain what your model is saying in plain language, you probably don't understand it well enough yourself.
And this brings us to what might be the most important takeaway from this whole discussion. So here's the crucial point. Regression is not magic. It's not an automated truth machine that you just feed data into. It is a framework for thinking. It's a structured way to ask questions of your data. But the quality of the answers you get depends completely on the quality of your questions, your actual knowledge of the subject, and having a critical eye when you look at the results.
And that is where we're going to leave it. The next time you see a headline or you read an article that claims a new study found a link between X and Y, you are now equipped to think a little more deeply. You can ask, what kind of model did they use? Are they maybe confusing correlation with causation? Is it just a simple line they've drawn through a really complex world?